Well, today we're going to do finish up the implementation of the list using the composite and state design patterns. And at the end of class last time we had introduced the max method. And this is going to illustrate the concept of a helper function. So let's take a look here in figure 6.30 at what the code is, and then I'll show you a snapshot of the execution of the code. The first method there in our list in figure 6.30 is the list version of max, and if the main program calls wants to know what is the maximum of this list, the list receives the request with the max, but the list says, I don't know what the max is, I don't even know if I'm empty or not. So what does the list do? It calls the what version. It returns what? Underscore what? Head arrow max. So it calls the max version of the node. And then, which max is going to get called? Is it going to be the empty CS node max, or is it going to be the non-empty CS node max? Well, it depends on what? Polymorphic dispatch. Okay, so if it's empty, the empty one will get called. If it's not, the other one will automatically. Well, if it's empty, there is no max of an empty list. So that's where we implement our precondition. Okay, so that violates the precondition. On the other hand, what happens if it's a non-empty node? Now, remember, what two elements are determine the environment when you are programming a method? There's two things that determine the environment. You are in a room and you are programming a method. You are in a room and you have access to what items in that room? What are these two things? What are the two things you have access to? Parameters. The parameters and the attributes. So what are the parameters of a non-empty node? Well, in this case there are no parameters, right? But what are the attributes of a non-empty node? Underscore data and underscore rest. Okay, so that's so now what the non-empty node version of max does, it says, well, it solicits the help of the max helper. So what it does is it calls so remember, it has underscore rest and underscore data. So it does underscore rest dot max helper. So now you see, when it's calling max helper, it's calling the max helper for whom? For underscore rest. Are you with me? Which is a what? What is underscore rest? What is it? It's a list, right? So it's calling, and then it's passing along, as the parameter is passing along data. So now, in the next part of the figure, so it's calling the list. So now what's the list version of max helper? Well, that data is being passed as what parameter? It's val, right? So what it does is it says, hey, I don't know, rest doesn't know if he's empty or not. So he says, what am I going to call? He said, I don't even know if I'm empty or not. So what does it do? It calls the node version of the helper. So it does underscore head is its head node, okay, and it calls max helper. And so now what happens is, the node version of max helper gets called. And which one gets called? The empty node version or the non-empty node? Well, polymorphic dispatch. Okay, so what happens is, if underscore head is in fact an empty list, then what does that max helper, then which max helper gets called? It's the empty one, right? And so if we compare val, and it has val, and so if we compare val, is well, I want the maximum of this value and what's in me, but I'm empty. So what's the maximum of this and a list and all the value in the list? It's just the value. So see, so it returns the val. But on the other hand, if the rest is not empty, now what? Now look. Now, what is the environment of when you are programming max helper, the non-empty node version of max helper? What is in your environment? Now, how many? So Yeah, it is three things, because it's the parameter which gets passed, and then it's your own what? your own data and your own rest. So what the max helper of the non-empty node does is it compares underscore data with val. And if underscore data is bigger than val, then what is the maximum? Well, data is bigger than val. Okay, but now we're not done because there's more of the list to compare it with. So what does it call? It calls underscore rest. It's underscore rest dot max helper of the data. But on the other hand, if val is bigger, it returns underscore rest dot max helper of val. So you can if you can kind of see how that works logically, that's good. But what we have here is a sequence of these environments. So let's take a look. In this environment, what we're doing is, this is in figure 6.31, part A. This is the environment of the initial call to the list. So let's suppose that I've indicated in here that the list is the list 27193. Now obviously, ultimately, what should get returned? What is the maximum one? It's 9, right? Now tell me again, what is this in C++? It's a what to the what? Pointer. A pointer to the current object. So do you see that this is a pointer? This is a pointer to the current object, which is a list. So star this is a list. So I've indicated what the elements of star this are, 27193. And you see that, and what is in the environment of the list? It only has a what? What is its attribute that it has access to? Underscore head. So there's its underscore head. It points to an abstract node. It doesn't know what kind it is. Are you with me? So this is when the main program calls mylist.max. That's the environment. And what did the main program do? It called what? The what version?
The non-empty.
Yeah, the non-empty version. The node version. The non-empty node version. Okay, now what's in the environment? So here's part B. So what is in the environment of a non-empty node? A non-empty node has a what? An underscore data and an underscore rest. So that's his environment. You see what we're saying? And we've noted here that now what is underscore rest? I've just noted here that the non-empty node doesn't know that it's 7193, but I've indicated that that's what it is. Are you with me? And so what does this head arrow? So now what does it do?
It does max helper.
Now it calls the max helper of a list. So notice that we're going to alternate. We have a list environment, and now we have a node environment. So now what's it going to call? It's going to call a what? What's the next environment when it calls? It's going to be a list. Are you with me? Does everybody see? So you see it's a list. So what does a list have? A list has what? What are the attributes of a list? It has an underscore head. So you see this list now that when we are in the list version of the helper, the list version of the helper, the list has underscore head, and it points to this abstract node. We don't know what it is, all right? But it got past what? It got past that val, which is the 2, which got passed from part B. You see, it passed the 2, so there's the 2. So now it has access to the 2. But now what does it do? It calls the what? Remember what it called? Right? So it calls the node version, but what does it give it? Do you remember what it gave it? The rest, it passed along the data, but then it did the what? Here, let's go back. So here it says return what? Underscore head arrow max helper. So it passed that value on, okay? So it's going to pass that value on, and now the next environment is going to be a what? A node. So here's the node. What does a node have? It has an underscore data and an underscore rest. Okay? Does everybody see? Along with that value that got passed along. Is everybody clear on that? So now we are in the non-empty node version of the helper. And now what does this node have? Now what can it compare? It can compare the what and the what? The 7 and the 2. The 7 in its underscore data, and the 2 is in the parameter. Are you with me? and it compares those, and because the 7 is bigger than the 2, it calls what? A list. Now, are we going to get back to a list environment or a node environment?
List environment.
A list environment. Okay, so it passes the 7 along as the value, all right? And now we are back in the list environment, but our underscore head now is pointing to the 193 because it does rest. See, it passes, it does rest dot max helper. See, underscore rest dot max helper. All right, so that's and there it is. And so, but now what does the list? What does this one do? He says, I don't know if I'm empty or not. So it calls the node, passes along the 7, calls the node. But now what does you see? It does. And so now that we're in the node, now that node, the underscore data is a 1, and underscore rest points to an abstract node. But now what does this node have? It has what can it compare? The 7 and the 1. Are you with me? So what does it call? So which one's bigger?
7.
The 7. So it passes the 7 along, and it does a list. So here, now we're back to a list environment. You see how that works? But now what does a list do? I don't know if I'm empty or not. So what does it call?
Node.
So in part H, we're back to a node, and now we can compare the 7 and the 9. And which one's bigger? The 9. And then it calls the what? It calls the list version. Okay, so now we're back to a list, and the 9 gets passed along to a list. All right, and now here's the head. And this is the 3. So we go in part J to a node version, all right? And so we compare the 9 and the 3, and we get a what? We go back to a list environment. And now what happens is, when we call underscore rest dot max helper, underscore rest now is what? It's empty. So that's going to, here, this is our list version, but what happens in L? Empty. And so it returns the 9. Returns back up the call chain. See? So you think about how those. I think it's helpful when you're programming with objects to think about. So when you are writing code, think about being in that little room and what you have access to and what the environment looks like. Okay. So now here is the code in Figure 6.32 is the code of toStream. Now you remember how a list gets printed out, like 4, 7, 3, like this. So it starts with a paren, and then each element has a comma after it, separating it from the last one, except for this last one that doesn't have a comma; it just has a right paren. So here's is the code for streaming a list to the stream to look like in this format. So what happens is, if the main program wants to know wants to print out the list, he calls in Figure 6.32, the first part here, toStream. The list version, what does the list say? He says, I don't know if I'm empty or not. So what does he do? He says, calls the node version. Well, which one is going to get executed? Well, if the list is empty, it's going to call the empty CS node. But what's it going to print out? Left paren, right paren, because it's empty. Are you with me? But now if it's not empty, now what? It's not empty, so it's not empty. So now what does the non-empty node print out? It prints out the what? The left paren. Does this make sense? And then it does, and this, okay, now we will leave it up to rest dot head, the toStream helper with giving OS, the output stream. Oh, right. Thanks for reminding me. Yeah, so it prints out this and this. Yeah, see, they are being grouped. Yes, yeah. They are being grouped like this. It prints out this and this. So now what's it going to do? It's going to print out a sequence of what? Commas and spaces in the next one. Commas and spaces in the next one. And then when you get to the end of the helper for this, it just has to print out the right paren. See how that works? So here's the helper. So the helper continually calls itself. This one is kind of interesting in that there is no list version of the helper. See, because the list version is responsible for this. We don't want another left paren. So you see what we're saying? So we don't have a list version, because the list version is what printed out that left paren. We don't want more left parens in here. Okay. So then if it's empty, it prints out this one. Otherwise, it prints out the comma, the space, and the next one. Pretty slick, huh? Look at that. No ifs. It's all just boom, boom, 1, 2-liners. I think that's just very nice. Okay. Next one is operator equals. Now, operator equals, I believe, is a homework assignment. Is that right?
Yes.
So what let's do is, instead of showing you, is it?
Yeah, it is.
I think, yeah, I think it is.
It's,
So what we're going to do here is, first of all, we overload the operator equals equals. This is so you can say like this. You can say if my list equals your list. You know, blah, blah, blah. This is so that by overloading the equals equals operator, that lets us do this. But what it basically does is, it's just a one-liner that calls the equals method. So it's left-hand side dot equals right-hand side. So now the question is, how do you write equals? And that's what your job is. So now here we have documented the preconditions for both the equals and for the equals helper. This is going to be an equals helper. So if we look here in figure 6.33, if we look at the code, there is an equals for the list, an empty node equals, and a non-empty node equals, right? And the documentation for equals is, the post condition is true is returned if this list equals list right-hand side. Otherwise, false is returned. And then another comment here, two lists are equal if they contain the same number of equal elements in the same order. Okay? And then these are exercises for the student. But then now now look, before we actually go on, let's take a look at what the parameters are, okay? So the parameter for equals for the list is the right-hand side. The parameter of equals for the empty node is the right-hand side. And the parameter for equals for the non-empty node is the right-hand side. Okay? But the parameters for the equals helper are different. So look, the parameter for the equals helper is, we have, for the list version, we have a first and a rest. And for the equals helper, we have a first and a rest. For the equals helper, we have a first and a rest. Okay, so that's one thing to notice, is that the parameters for the equals helper are different than from the parameters for the equals. And so now whenever for our documentation for this, we have to explain, well, how do these parameters work? What is the post condition? So the post condition for equals helper is true is returned if first equals this arrow first and rest equals this arrow rest. Otherwise, false is returned. So once you get to a helper, what do you know? We know that we are comparing the first and the rest with the list. We're given a first and a rest with the list. On the other hand, when we're here on the not the helper version, but the original version, what are we given? We are given a list. We are comparing a list with a list. Do you see the difference? Here in the original, we're comparing a list with a list. But with the helper, what are we comparing? A first and a rest with a list. Do you see what we're saying? So we're giving a first and a rest. Does everybody see the idea there? Okay. So the post condition is if first equals this arrow first and rest equals this arrow. So you see the first and rest are unpeeled. They get peeled off and they get sent as parameters to the helper. Is everybody clear on that? So look, what I've done here is, so no code, but here's what the code has to do. So if we can understand what this code has to do, then we can program it. So check this out. This is a trace of my list dot equals your list, where my list is 417 and your list is 4. Now obviously in the end, are these lists going to be equal? No. But what it's going to do is it's going to compare what? It's going to compare the 4 with my list with the what? The 4 of your list, and potentially they are equal. But then it will compare the what?
Rests.
The 17, the rest of my, with the what? With the empty list. And those won't be equal. Are you with me? So you see? Okay, so that's going to be the scenario. So here's what happens. The main program calls is equal, okay? And we start off with the list version of equals. All right, and it's because we're in a list, what is the environment of a list? What is its attribute? Underscore head. So in part A we see underscore head, and then what else do we have? A parameter, right? So that's right hand side. Now it's a little. I didn't use different graphic, but you understand that the right hand side up there, that cloud, that is a list, whereas the cloud below it that underscore head points to, that's an abstract node. Are you with me? So there's a subtle difference there. Okay, so but at any rate, all we know is all we know in this environment is that our parameter is right hand side, and that is some list, and underscore head is a pointer to an abstract node, and I've indicated here what they are. The right hand side is the list 4, and star this is the list 417. Okay, so now what does that method call? It calls, what did it? Oh well, we don't know what it's going to go. We're not tracing it. I mean, we don't have the code to see what it calls. But what should it call? It'll call the non-empty node equals. And what will it pass to the non-empty node equals? It will pass along what? Yeah, the parameter will be right hand side, and when it calls it, the environment of the non-empty node will be 4, and its rest and its underscore rest will be the 1 and the 7. Does everybody see how that works? Okay, so you have to come up with the code to do that. I haven't showed you the code here because that's the assignment. Okay, so now, and here again, what will this non-empty node do? It will call the what? It will call a list for the helper, right? And it will pass along what? So here's the list equals helper. So now what does a list have? What is the attribute of a list? Underscore head, right? So there's underscore head. And then what got passed along here? This shows you what gets passed along is the parameters, you see? So what's getting passed along is the parameters. First and rest. Are you with me? So at this point, rest is 17, this is 4, and that's our list equals helper. But now what will the list do? The list version always calls the what? The node version, all right? So it will call the node version. So this is the non-empty node equals helper. All right? So now now here's where we're going to finally make a comparison. The non-empty node equals helper is going to have what? Because it's a non-empty node, its environment is an underscore data and an underscore rest. The parameters are first and rest. So now what can it compare? First and underscore data. And if those are not equal, right away you know what? Yeah, you return false. But in this case they are equal. So now what happens? In this case they are equal. So now what are we going to call? Now comes the composite pattern. Because how is it that, so how do we know if these lists are equal? They are equal if what? Because we know that the 4s are equal, so now what do we call? The what? The list version, we see if the list, we're going to call the list version of equals, not the helper, but the list version. And so it depends on what? On whether what? Rest equals underscore rest. So now we're back to the very top level. You see? Now this is composite. We can treat those as, because they are lists. So now we can make a recursive call and say, oh, if these are, it's equal if these two are equal. See? So now we're making a call as if we were the main program. We're going back to the beginning, as if we were the main program. You see what we're saying? So is all we have to. So now it's list equals. But now the right hand side is going to be the empty list, and star this is going to be 1-7, and we're in the environment of list with an underscore head. But now these lists are shorter by 1. Okay. So now what does the list version do? It calls the non-empty node equals. Okay. And so now. The non-empty node equals has a 1, and so now the underscore rest is the list with just 7 in it. But now, you guys, what is underscore rest? Underscore rest is what? It's the 7. And what is the right-hand side? The right-hand side is empty. All right. So what this non-empty node will call is it will call the list equals helper, and it will pass along the 1. See, let's go back. See, the 1 from underscore data gets passed along as a parameter. Are you with me? And now, and so this is the list equals helper. But now the list calls the what? The list calls the what version? Node. The node version. So here, so the empty node equals helper now has first got passed along as a parameter, and rest is 7. Right? But now this is the empty node. Now look. This is the empty node equals helper. But what is this empty node being given? Well, what is a parameter? What's he being given? First, which is 1. He says, gee, so what's he going to return?
False.
Yeah. It's going to return false. Because it's asking me if 1, is equal to my first, but there is no first. So, they're not equal, so you return false. So the code is deceptively, short. It's deceptively short, but if you just get this idea, so anyway, that's the story of how equals works. Yeah, question?
How do you compare?
No, you never do. You are only going to compare underscore datas with parameters. And they are all of type T, and the precondition for all of this to work is that type T has the comparison operators. So they could be doubles or ints or whatever.
But aren't you comparing first with a node?
No, you don't compare. You don't have to compare first. Are you with me? Because there is nothing to compare it with. But if you have been given this, you know that if you have been given this value, which is the first part of the other list, and you are empty, you know that these lists are of non-equal length, and you don't have to compare it with anything. You know it's just false. You just return false. That was a good question. You see what I'm saying? There's nothing to compare it with. But you don't have to compare it with anything, because you know the lists are not equal length. So this other list was longer than I am. Yeah, so you just return false.
Yeah.
Okay, so let's take a look at some methods for construction and insertion. Now for these, we're going to take a look at the constructors, and I've written all the constructors for you, and we have an example of how to use them. And now I think I put this figure in figure 6.36. I think I put this figure on the board yesterday. Somebody was asking, what is an empty list? Look, here is a picture of the empty list using the composite state pattern. It's not that underscore head is the null pointer. Instead, what does it point to? An empty node. All right? So look at the constructor. This matches the code for the constructor. See, we have list CS, : list CS. So that's the constructor for a list. And what does it do? It does, oh, it does what? What is that colon, and then we postpone the brace? That's called the what list? And what is that called in C++ when we have the paren, when we have the variable in the paren, the variable in the paren, the variable? What's that called? What's that called when we had, you know, when we postponed the brace?
Initializer.
Initializer list. That's an initializer list. So what is that saying? That's like saying what? Underscore head what? What's that equivalent to? Gets new empty CS node T. So see, that's what that does. Are you with me? So new lists are initialized like this, so no more null pointers, okay? Okay, so now that's when the constructor is given no parameters. Now the other ones, there's 3 more constructors. And each one of these constructors are given different things, okay? And none of these constructors allocate with new. And so in this next constructor, we have, if you give a constructor a pointer to a node, it just sets underscore head to that node that you give it. All right, that's one constructor. Sorry, this is the constructor for a non-empty node. All right, so what does a non-empty node have? What are the attributes of a non-empty node? Underscore data and an underscore rest. So what it does is it just does underscore data gets data. So it just sets.
That's not a constructor for a list of elements.
No, now this is a constructor for a non-empty node. Yeah.
Parameter gets.
That is a very good point. And the answer is yes. This is actually called function overloading. This is another example of function overloading. The way function overloading works in C++ is the compiler looks at the types of the types and the numbers of the parameters, and if you have 2 different functions with the same name, but one has a different signature, different parameters, it will match the parameters with the parameters of the other function with the same, and use that one. That's the idea of function overloading. Yeah.
Can you call a list constructor with a node constructor inside of it, or do you have to create a node and then create the node?
Okay, these constructors all assume that you've created the node.
Okay.
Okay. So, and I think there's some comment here to that effect here. So here's 2 more non-empty node constructors. All right, and notice that neither one of these non-empty node constructors does new. All right, and so the post condition for this next constructor is what do we give it? We give it a data. We give it a data and a what? A pointer to a node. Are you with me? And so it sets. And so what it does is it sets its underscore data to the data that it's been giving, and it sets its underscore rest dot underscore head to the node. And with this next one, what are we giving? Instead of giving it a data and a pointer to a node, what are we giving it? We're giving it another non-empty node. And it does, what it does is it sets its underscore data to it duplicates it to the right-hand side dot underscore data, and its rest, it duplicates it to right-hand side dot underscore rest. Okay? So these are 2, so these, and notice that we have this comment up here with the first one, underscore rest owns node and is responsible for garbage collection. So we're going to do some I'll show you an example of how these constructors get used. Now comes the next really a big technique that we're going to be using again and again. This is called the owner parameter strategy. Now, what we've done so far is we haven't, equals doesn't change any of the lists, right? But are these lists that we're working with mutable or immutable? Are they mutable or immutable?
The state when they're mutable.
The state, they are mutable, so they can be changed. So for example, if you want to remove, if you do a rem first, remove the first item from a list, and that list only has 1 item in it, then that list becomes the what? Has to become the what? The empty list. So its state has to change. But the question is, if the list calls the node version, are you with me? Look, if the list calls the node version of rem first, and the node, and it says, oh, I need to change, what does that node have to do? It has to change what? It has to change the head of the list that called it. Do you see what we're saying here? It has to change what called it. So this is the concept of the owner parameter strategy. So when you are in the, because look, when you are in the environment of if you are in the environment of a node, how are you going to change the underscore head that's pointing to you? You have to have access to it. Do you see what we're saying? So therefore, it has to be passed as a parameter. So that parameter is called the owner. So some methods require that the state of the list changes. The state of a list changes by changing what the head of the list points to. If the node version of the method needs to change the state of the list passes itself as the owner to the node version of the method. Now, does everybody see the concept there? Because and here again, this is easy to understand if we get the concept of what the environment is. Because you see, a node, if you're in the environment, if you are in a non-empty node or an empty node, how do you know, how are you going to change the pointer that points to you? It has to be passed as a parameter so that can be in your environment so you can access it. All right. Now, what we're going to do is we're going to illustrate this with prepend. So figure 6.37 is prepend. Now check this out. So, and here we'll have all the code for this. So look at this. In prepend, so you know, the main program's calls, say, it calls prepend, and it says, say you want to prepend the list out of the element, I don't know, 50. So then data will be 50, right? Okay. And so, but what does head do? It says, oh, I don't even know if I'm empty or not. So what does it do? It calls the what? The node version of prepend. Are you with me? It calls the node version of prepend. But look, not only does it pass data, what else does it pass? Look, on that first argument, what else does it pass? What is? Yeah, and what is this? Pointer to the list, the pointer to the current object, which is the list. So star this is the what? The list itself. Are you with me? Now look, that's the formal parameter. Star this is the actual parameter. Now, what's the first parameter of the node version? It's called what? Owner. Are you with me? Do you see here is, so that star this is the actual parameter. Owner is the formal parameter. And so you see this assertion here, assert. Owner dot underscore head is this empty CS node. Are you with me? Because now we're in a node, okay? And so look, check this out. So if the list is empty and the main program wanted to insert 50, then that 50 gets passed on as data, and owner dot underscore head is this empty CS node. So therefore, what does owner? So what does the empty list do? What does it change? It does what? But look at the code for prepend if it's not empty. It's the same thing. So look, how does this work? It works like this. We're going to do two traces. Let's do a trace of mylist.prepend 6, where mylist is 834. So what should it do? It should be 6834. But now how does the call sequence work? Now look. So here, the main program calls prepend 6. This is mylist.prepend 6. So 6 is data that's being passed along. Underscore head is a pointer to an abstract node. Are you with me? And what does this call? Which version? The empty node version or the non-empty node version? The non-empty node version. So what's the environment of a non-empty node? It has a data and a rest. But now look, not only does it have 6, which is being passed as the data, it also has access to what? owner. No, look. Well, yeah, data, underscore data, and yeah, you're right. Not only does it has underscore data and underscore rest as its attributes, but what does it have as its parameters? The data and the what? And the owner, because that got passed. Do you see? So now it has access to what's pointing to it. So what does it do? So we do head, arrow, prepend, star this data. So now there's the and by the way, what is this? It's a pointer. What is always this? Pointer to the current. So you see, this is pointing to this node because this is an. Are you with me? And so now, do you remember what the assignment was? It was owner.head gets new non-empty node data this. All right. Are you with me? So what is this? When we do new non-empty node, what does that do? That sets up a new non-empty node, right? And this is the constructor, and what are we giving it?
Data.
A data and a node. This is a node. Are you with me? And it returns the pointer to that. And what the constructor does is it sets underscore rest to this, and it returns the pointer. So owner points, and so owner points to that new returns the pointer to the newly allocated node, and it does, because it does owner._head gets this, then owner._head points to that newly allocated node. You see how all that is all just one line, lots going on behind the scenes. But look, it's the same thing. It's the same code. Here's a trace of mylist.prepend 6 where mylist is the empty node. So watch this. It's the same thing. So here's the environment of, in part A2, here is the environment of the list, the original list. The main program gave it data, which is 6. Underscore head is a pointer to an abstract node. It doesn't know whether it's empty or not. So now it calls the what? Now it calls the empty version, the empty node version. But what does the empty node version have? It doesn't have an underscore data or an underscore rest because it is a what? It is an empty node. This is pointing to itself. Are you with me? And it has owner, which is pointing to itself. It has access to owner, which is pointing to this. And if you do the exact same, look, if you do the exact same code, it does the exact same thing that it did here. With this, with the last one pointing to the empty node, pointing to itself. Yeah, I think these pictures are really. Yeah, I think these pictures. It's a way to. It's object-oriented programming is a big deal, and I think it's really crucial that you have a picture, a visual picture of what's going on. Okay, for the remainder of this lecture, we are going to use this. I've produced this screencast of the material. So the next method we want to look at is copy head. So figure 6.39 shows the code for copy head. And as usual, we have the first version of copy head is the list version of copy head. And notice that copy head, as with list L, it returns a pointer to a node. In this case, a pointer to an abstract composite state node. So, and then the second version is the empty node version of copy head, and then the third version is the non-empty node version of copy head. And we see what happens is if a calling program wants a copy of its head, a copy of the right-hand side, then the list version does not know whether it's empty or not, so it does not know what to return. So it simply calls the node version. Now, which node version gets called, the empty one or the non-empty one? Well, again, it's by polymorphic dispatch. So if the right-hand side is empty, then we are calling the right-hand side dot head arrow copy head is calling the empty node version. And so what the empty node version does is it knows that it's empty, so to make a copy of itself, it returns a new empty CS node. So that is a simple one-liner. But on the other hand, if the right-hand side is not empty, then right-hand side dot underscore head arrow copy head will call the non-empty node version. Now here the non-empty node version does the copy recursively, and it is a single it creates a single new non-empty CS node from the heap and returns that pointer to it. And because it's calling a new non-empty node with the parameter list that has two parameters in it, and what are those two parameters? Underscore data, which is of type T, and underscore rest dot underscore head arrow copy head, and remember, copy head returns a pointer to a node. So this is using the constructor that takes as parameters a data and a pointer to a node. So if we come back to figure 6.36 on this slide, it is the first non-empty CS node constructor that takes as a parameter a data of type T and node, which is a pointer to an abstract CS node, right? And basically what it does, remember there's no new in this because there's the new was done in the calling constructor. And what it does is it sets the data that we give it, it sets its underscore data to the data that we give it in the parameter list, and it sets its underscore rest dot underscore head to be node that gets passed as its parameter. So let's go back to the code. When we return rest dot underscore head arrow copy head, that is a recursive call to copy head. So the whole thing happens all with no loop, and it's all done recursively. Okay, the next group of methods are methods for destruction and removal. Now, the next method that is a homework assignment is the Remlast, which is the code here is shown in figure 6.41, and we'll do another little snapshot of the sequence of events of calls that happen to do Remlast. So first let's take a look at Remlast and then Remlast Helper. So the precondition for Remlast is that this list is not empty. So if you try to remove Remlast from an empty list, that should be a precondition violation. And then the postcondition is that the last element is removed from this list and returned. So notice that Remlast returns of type T. So again, in the Remlast there are three methods. There's Remlast for the list, there's Remlast for the empty node, and there's Remlast for the non-empty node. And now look, here is another situation where a node, if you are in the environment of a node and you want to do Remlast and you are the last node, you have to have access to the owner, because in order to change the state of the owner, in order to remove yourself. So those are the three methods for Remlast. The method for the list, the method for the empty node, and the method for the non-empty node. But now look at here, we also have, this uses a helper, so that we have Remlast Helper. Now, the Remlast Helper has a different set of pre and post conditions. The precondition for Remlast Helper is that previous dot rest is this list. So now in the helper, the immediate list, for the list, the previous dot underscore rest is this list, and the post condition is the last element of previous is removed and returned. So here, so how in the world is the Remlast Helper method going to have access to previous? Well, it's passed as a parameter in the parameter list. So you see here, for the Remlast Helper for the list that returns type T, its parameter is, it gets a parameter named previous. Okay, so there's one parameter. But now it's a little bit more complicated. For the nodes, both the empty and the non-empty node, they have two parameters. They have owner as well as previous. So why in the world do we need owner as well as previous? Well, what's going to happen is
previous is going to be the list previous to the owner, and then the owner will be the list that owns this node. So let's take a look at the snapshot of an execution trace. So here in figure 6.42, we start off and we assume then, and again, we're not going to give the code because that is an exercise for the student, but the code is, the main program wants to do remlast of a list that is 95468. So eventually it should remove the 8 and the list that should be 9546. Okay, so here we are on the list, and what is in the environment of a list? Well, it just has an underscore head, which is a pointer to an abstract node. All right. So then what happens is, in part B, the list calls the node version, and it passes itself. It passes itself as the owner, and so now we are in a non-empty node, in the non-empty node environment. And of course, the first node of the list is the node that has an underscore data of 9 and an underscore rest that points to the rest of the list, and the rest of the list is 5468. Now let's pause here for a moment and think what would happen if we were in the, if the empty list got called, if the empty node were called here. If the empty node were called here, then what would happen? Well, we would be trying to remove the last item from an empty list. But there is no last item in an empty list, so that would be a precondition violation. But in this case, it's not a precondition violation. So now what does this non-empty node do? So now what happens is the calling pattern is going to be that the helper continues to call the helper. We don't ever go back to the original list call. Okay, because we don't want to have the possibility of a precondition violation. Now that we know that the precondition hasn't been violated, the helper, so here's another clue for how to do the code, the helper versions of Remlast call the helper versions of Remlast. So now, what does this non-empty node do? He doesn't know whether rest is empty or not, right? If rest is empty, then this node should be deleted. But if rest is not empty, it should not be deleted. So what do? We call a list, the list version, the list helper version. And what do we pass? What does this figure part C of figure 6.42 show? Well, first of all, we are in the environment of a list. So what does a list have? It has an underscore head. And what is the underscore head of this list? It is the rest of 9. So that is the underscore head of the list. And you should make the call so that previous is what we used to call the owner. But see, well, and you should make the call so that previous is pointing to this list. Now then, what does the list version do? The list version calls the node version. So in part D of the figure is the environment for the non-empty node remove last helper. And now we see why we give the names of the parameters previous and owner, because in this environment, now we are in the environment of a non-empty node. So what are the attributes of a non-empty node? Underscore data and underscore rest. Okay, so in this environment, our underscore data is 5, and our underscore rest points to the rest of the list, which in this case is going to be 468. And who is owner? Owner points to us, points to this node, and previous points to owner. So that's the difference between previous and owner. All right, and so then what happens is this non-empty node, because we are non-empty, then there's no action is to be. We have to work our way down the list. The only time that the action is going to be taken is whenever we are in the environment of an empty node. So what does it do? It again calls the list remove last helper, and it sets it up so that previous points to the node for which we are the list, and underscore head is our underscore head. Now compare part E of this figure with part C. You see what has happened is we have worked our way down the list. So it's the same environment, it's the same kind of environment where our attribute is underscore head and previous points to the node whose underscore rest is us. Okay? And then, so it continues down. So in part F, we work our way down the list one more time. And again, owner is the is a parameter that we have access to. So because we are in a non-empty node, our attributes are underscore data and underscore rest. And then on it goes. So again, list G is like part G of the figure is the list remove last helper, and we are working our way down the list. So now compare part C with part E with part G, and then imagine what would happen then if once we get to an environment that corresponds to figure F. If we are empty, what needs to be done? And I'll give you a hint. It's a very simple way to do this is if you code rem first, then you can actually use rem first in rem last. So that's a little hint. Okay, the next group of methods are methods for manipulation. And now here in this next slide is a key difference between how we use a first in list CS and how we use set first in list L. In list L, we have a method called set first. And the way we use set first is if we have a mylist, which is a list L, if we say mylist.setFirst 99, then the purpose of set first is to set the data of the first node in the list to 99. But in list CS, we do not have a set first method. Instead, what we do is we overload the first method. And so, the way because we overload the first method, we don't need set first. So the way you would do the same processing in list CS is if you want to set the first element of your list to 99, there is no set first. You say your list dot first gets 99. So the dot first can be used, even though it's a method, it can be used on the left-hand side of an assignment statement. So in figure 6.43, we have REST, the implementation of REST. And the way REST works is, again, we don't know if the main program wants the rest of a list, it calls the REST method for the list. But of course, the list only has an underscore head. It doesn't know whether there is a rest or not. Of course, if there is no rest, then that's a precondition violation. So the empty node version of REST implements the precondition. And then on the other hand, if it's non-empty, then the non-empty node has two attributes, an underscore data and an underscore rest, and it simply returns underscore rest. So now reverse, and so the last method that we're going to describe in this screencast is reverse in figure 6.45. And here again, reverse has a helper. And the details of how this, the details of the algorithm for reverse are given in the text in chapter 6. But basically what it does is it uses a helper, and it uses a very clever idea. There is going to be an auxiliary list, and to show this, in the next slide to show this, we have this diagram that has this and rev list. So what the algorithm does is it sets up an auxiliary rev list that starts off to be empty. And what it does is each time it makes a recursive call, it takes the first element of this and it prepends it to rev list. So you see on the first line, the 9 is peeled off from this and it's prepended to rev list. So that gives us the 2, 4, 7, 3 and the 9. And then the 2 is, so we rem first the 2 from this and we prepend it to the 9. So that gives us the 2, 9 and leaving us with the 4, 7, 3. Then the 4 is peeled off, making the rev list 4, 2, 9 and leaving us with 7, 3. And then the 3 is peeled off and put in front of the 7, 4, 2, 9, leaving us with the empty list. And then the rev list, and then what we return is rev list, this auxiliary list. So that's the idea. Those of you who have taken programming paradigms, this is basically the reverse onto in scheme that we did. It's the same, it's the exact, so you have a little bit of an advantage in knowing how this algorithm works. So let's take a look, let's go take a look at the code in figure 6.45. The post condition is that this list is reversed. So the main program just calls reverse with no method, with no auxiliary, with no parameter, okay? And then, of course, the list, what the list is going to do, it's going to just turn around and call the node version of reverse, all right? But now look, the node version of reverse has an owner, so you should know now what the actual parameter for owner is going to be. All right, and now let's take a look at the post condition of the reverse helper. The post condition is this list is prepended to rev list in reverse order, and this list is empty. And you see now the parameter that gets passed is called rev list, okay, to the reverse helper. And you see now the reverse helper, the list version of the reverse helper, is going to call the node version of reverse helper, but with what? But with 2 parameters, an owner and rev list. You should program that to do the operations as shown in this last slide with this and rev list. Okay, and there are more details, a few more details of how all of this works in the text, and this will conclude our screencast.